Okay, what's up, folks? So now I'm gonna do the decoder portion of UNet pixel space. Okay, so let's get started. So just picking up right where I left off the last time, right? So we have our downsample, which is a stride of 2. It's a convolutional. It's a 2D convolution with stride of 2. Okay, right. So in the last 2 videos, we did the training loop for rectified flow, right? So we have our training loop, this nice tight loop with that where we call this compute data function that does our rectified flow, right? We have an image, we sample from a standard normal, we compute our image along the trajectory, we compute the ground truth, which is the derivative of that trajectory, that straight line, we pass it to the model, which gives us a velocity, and then we do the squared L2 norm of that velocity, and we backpropagate on that loss, right? Just like I showed in the notes. We're just computing this expectation. And then now I coded up the encoder for the backbone. We're just using UNet. We chose to use UNet with ResNet blocks, right? Because we're doing celeb A faces. So it's a small amount of data. So we're using a model that has inductive bias, and we're using UNet because the skip connections passed from the encoder to the decoder will give us good velocities. Okay, so we coded the encoder last time, right? So we're downsampling and we're convolving, right? And I'm only downsampling on the last 3 portions, right? So now in the middle portion, we have something that's B 1024, 4 and 4, right? Because our original image size is 32. And now we're gonna code the encoder, right? So we're just gonna call upsample and ResNet blocks, okay? All right, so first thing I need to do is, because we need these for skip connections. Okay. Now, okay, I need to make four is going to be, so it's going to take in the mid. It's going to upsample it to 8, 8. In this way, we can concatenate it with D4. Okay, so upsample 1024. ResNet block 1024 plus 1024 to to 1024 time dim P dropout. Okay, so so this is going to be, gonna take in torch.cat. Up 4, E4 along the channel dimension, so that's 0, 1. Right, so it's taking in something of 2048, and then it's passing out something of 1024 that's upsampled, right? So we upsampled the mid, and we're attaching, so now we're concatenating it along the channel dimension. So, right, that should give us that. So let's run this really quickly. So we have our main method, right, where just like in the last video, I have xt is my image of shape 433232. I'm sampling a time step scalar. I'm creating the model, and then I'm just calling this on our image and our time step. Okay. So it doesn't like this. Torch.cat is not called properly. Okay. This should work. Oh, right. I need a time step embedding. Decoder 4 is ResNet block. So we have this and TM, which will project it out the shape. Okay. That's good. So from now on, I'm just going to do it like this. Okay. Boom. All right. So the next one is going to be 16, 16, right? So up 3, it's going to be on U4. This is going to be on D3. This is going to be D3. Okay. Okay. So 512. So up 3 is going to be called on U4. So it's going to bring this 1024. So this is going to be 1024, 16 by 16. So we're going to have 1024 here, and then D3 is 512 channel. So this is going to be 512, and we're going to bring this to 512. Okay. So up, so we have up 3, decoder 3. Okay. This looks good. Let's run this. It should be 4, 1024, 16, 16. Nope, doesn't like that. Oh, wait. First of all, it should be 512. D3, U4, so I'm calling up 3. So this is in upsample. It's complaining about upsample. Oh, it's complaining about the groups. Given groups 1 to have 512 channels, we got. It's complaining about the groups. Wait, is it complaining about the groups? It's an upsample. Oh shoot, let me set a timer. Make sure that I don't go too far over, okay? All right, let's break this up. All right, let's put this here. Okay. U4 dot shape. Yep. Up 3. 512. Oh. Yeah, okay. I guess it should be. Yeah, because I'm calling up on the previous. Yeah, okay. Yeah. Duh. Duh. Okay. All right. 4, 5, 12, 16, 16. That looks good. Boom. So should be 2024. Just undid all of that. Now, this took a D3. And this is going to be D2. This is going to be U3. This is U2. This is U2. This is D2. This is up 2. Okay. So now, up 2 is going to take in U3, which is, it has 512 channels. Okay. And decoder 3, sorry, decoder 2 is going to take in up 2, which is 512, D2, which is 256, is going to be 512 plus 256, 256. And we need to bring this up to 32, 32. Okay, so it should be 256, 32, 32. Yep, looks good. Then the next one, we're gonna take D1, so we don't need to upsample it anymore. So we don't need this, but we do need to concatenate U2 with D1. So U2 is 256, D1 is 128. $256, 128, 128. So it should be B128, 32, 32. Okay, perfect. Okay, now we need to have self.out self.out U1, which should be B3, 32, 32. So this is our velocity head. Okay, so we do conv 2D 128 in channels, kernel size 3, stride 1. Actually, no, not kernel size 3. We're not gonna convolve it anymore. It's just a pass through. It's just to give us our velocity prediction, right? So it's just a one-to-one mapping, it's just a one-to-one, 1 pixel to a velocity. And right, we're just gonna take all the channels, right? We're gonna take all the channel information and send it to a velocity. Okay. That should be B3, 32, 32. Let's call this out projection. Okay, now this is our UNet. This is our UNet. So this is it. Nice and neat. Nice, beautiful model. Very cool. Feels very good to code these things, folks. I hope all of you watching my videos one day get to experience the pleasure of being able to code fun neural networks, complex neural networks. It's very fun. And then the more you learn, the cooler models you can build. It's a lot of fun. It's a lot of fun. I didn't get to do all this in school. So I urge you to do your own self-study, because that's when you're really gonna get to do all the fun, state-of-the-art stuff. This isn't state-of-the-art yet. Well, it is. Rectified Flow is state-of-the-art, but you see how we're using something state-of-the-art with something fundamental. All right, let's just run our training code. Let's see what happens. See what happens. Let's look at our magnitudes, see if they start to move closer to our ground truth. Yep, it's moving up. Hold up, I don't like this. Let's look at it's taking too long. I want to sample size 32. Batch size 4. Let's do batch size 8. Let's do batch size 4. Okay. Boom. Let's see what happens. should see it steadily climb even for this small network. So it looks good right now. So we're going to see some stochasticity, we're going to see some noise, we're going to see some randomness, but we should see it steadily climb up, maybe hang around 0.5, 0.6 for a while. Or we should see the predicted velocity steadily climb up. Oh. Am I printing, not writing? Yeah. This is looking okay. This is looking okay. For a small sample size, yeah, I like this. I like this. I think this is good. Where are we at? 14 minutes. Yeah, let's stop this one. And then we'll do inference next. But I like this. I think these numbers look good. We'll know once we move it to the VM for certain. Maybe we can get, maybe I'll be able to sample. How much time? 14 minutes. Let's leave it at that. Let's leave it at that. All right, let's stop this video here. In the next video, I'm gonna fill out this sampling function right here, and where I'm gonna uncomment this and then sample some values. Cool. Thanks for watching.